Hello, this high-level overview is a revised version of a video that I uploaded some 6 years ago, so it will be more up-to-date than the first one, obviously. We'll check out the concept and architecture of NetApp ONTAP clusters. And let's start with a single node, which actually is a controller or machine that has the standard features of random access memory, CPU, network cards, and maybe fiber channel adapters all on board. In addition to that, a node also has a non-volatile RAM solution in the form of NVRAM, NVMem or NVDIMM, depending on the controller type, but all three solutions serve the same purpose. Data that enters RAM will immediately be copied to the non-volatile environment, after which the client is acknowledged that the data is safe, even though it's not on disk yet. We'll concentrate on that later when we deal with Waffle or the Write Anywhere file layout. But it's important to realize that every controller has a non-volatile RAM environment. And next to this non-volatile solution, a node also has a compact flash on board. This compact flash contains the operating system, which is called ONTAP. And this CF card has room for two versions of ONTAP. So after an upgrade, you have an active and an inactive version of the operating system, until the next upgrade, when the old version will be overwritten with the newer version and the current active version will become the inactive version. And finally, controller also offers the possibility to connect to the system even if the operating system is down. In the older systems this would be the RLM or the BMC, and in the current systems it is a service processor which is accessible via a separate IP address. So you can reset your system or connect to the console from within this service processor. And of course, a node will have hard disk drives or SSDs or a combination of the two. And these drives can be part of the node itself or in external disk shelves that are connected to the node. We'll talk about physical storage later. Let's first concentrate on what an ONTAP cluster really is. Now, an ONTAP cluster can be as small as a single node. So you may think, well, a cluster is always a collection of computers, isn't it? Well, that's true, but NetApp says that a single node can form a cluster all on its own and is regarded to be a single node cluster, which is fully functional with all available protocols for NAS and SAN. But it really is a single node. Now, obviously, when you run a single node, you miss the advantage of non-disruptive operations or non-disruptive upgrades, for example. So if you upgrade a node, that will result in downtime. And also, when the node fails, you lose access to your data. But still, you can run a single node cluster, which can be expanded on the fly, by the way, by adding a second node. And when that happens, you will have something which is called an HA pair, or a high availability pair. When running an HA pair, you do have the advantage of non-disruptive operations. And in the case of a node failure, the other node will take over the storage of the node that has failed, and allow clients to keep on accessing the data using the available protocols. Currently, the absolute maximum number of nodes in a single cluster is 24, or in other words, 12 HA pairs. This means that next to a single node cluster, you can have up to 12 HA pairs. So this is always an even number of nodes. So 2, 4, 6, 8, etc. So it's either a single node or a collection of HA pairs. There's a bit of a catch here. A 24 node cluster is only possible if you use NAS protocols like NFS or SMB. But if you use SAN protocols like Fiber Channel or iSCSI or NVMe, in that case the maximum number of nodes is 12, so 6 HA pairs. Now let's have a closer look at the HA pair. The two nodes in a single HA pair allow for non-disruptive operations because both nodes are physically connected to one another and to the disks that belong to the HA pair. So if one node fails or is no longer available for whatever reason, the other node in the HA pair takes over the disks of its partner, so clients will still be able to access the data. This is realized as follows. The nodes are connected in two ways. First, there is something which is called the HA interconnect, which is nowadays realized by two point-to-point cables between the two nodes. It used to be realized by plugging both nodes into the same backplane of a single chassis, but modern systems use external cables. This means that the two nodes of a single HA pair do not need to be in the same chassis anymore. This HA interconnect is primarily used to mirror the NVRAM from one node to the other and vice versa. So if a failover will have to take place, the partner will have the data in NVRAM. It will copy it to RAM and the data can still be written to the disks. Obviously, part of the failover is that the surviving node takes over the disks of the node that goes offline. So to make a long story short, a node that receives client data will copy the data not just to its own NVRAM, but also to the NVRAM of the partner. So in the case of a failover, the data will not be lost. The second way these two nodes are connected is via a dedicated and private network, which is called the cluster interconnect. This is the network via which all cluster configuration and more is shared among the nodes in the single cluster. So with a single HA pair, you can have a second point-to-point cabling next to the HA interconnect, or they can even share the same ports. But if you run multiple HA pairs, then you will need a switched network. And as you can see in a cluster with multiple HA pairs, each HA pair has its own HA interconnect, but the cluster interconnect is shared by all nodes. Now, as stated, the maximum number of HA pairs is 12 when you run NAS protocols. Now, these HA pairs are all interconnected by the cluster interconnect, and each of these HA pairs is a storage failover pair. So the disks of node 1 can be taken over by node 2 and the other way around. And the same goes for node 3, node 4, etc. It's important to realize that the disks of node 1 cannot be taken over by node 3 or by any other node than by node 2. And this holds true for every HA pair, obviously. But all HA pairs are interconnected by this cluster interconnect, and together they make up a single cluster. Now I hope you see that with regards to the cluster configuration and heartbeat, and other things we will see later, this cluster interconnect is a very, very important network. Without the cluster interconnect, there would be no cluster. So even with a single HA pair, this network is vital. And the only cluster that does not need a cluster interconnect or an HA interconnect is a single node cluster. And finally, next to expanding a cluster by adding new HA pairs, you can also unjoin nodes. And like adding, it has to be in pairs. So when you unjoin a node from an HA pair, you will also have to unjoin the partner node. So when you add nodes to a cluster, this is commonly referred to as scaling out. And when you remove nodes from a cluster, that's referred to as scaling in. Now let's have a look at storage. From the top down, data is stored in flexible volumes, which in turn live inside an aggregate, which is built up of RAID groups. And a RAID group is a stripe of drives. Flexible volumes can be grown and shrunk automatically or manually. And the data in the volume can be a collection of files and directories or LUNs, or even S3 buckets. However, an S3 bucket needs multiple volumes that together form a flex group, which can provide you with some 60 petabytes of data. Now back to regular flexible volumes. Flexible volumes are created inside an aggregate. An aggregate is made up of one or more RAID groups with parity disks. So to make a comparison, a RAID group can be regarded as a stripe. But in ONTAP they are called RAID groups. A single RAID group consists of multiple data drives and 1, 2 or 3 parity drives. A RAID group with a single parity drive is called RAID 4, 2 parity drives is RAID DP or dual parity, and 3 drives will give you RAID Tech, which stands for triple erasure coding. And obviously in an aggregate that has RAID 4 as the RAID type, you can lose a single disk in every RAID group. You can lose 2 disks with RAID DP and 3 with RAID Tech in each and every RAID group at the same time. Now please pay attention. Every node in the cluster has a minimum of 1 aggregate, and this first aggregate is a root aggregate. And this single and mandatory aggregate has only 1 volume, which is called vol0. This volume holds the configuration, the log files, backups of the configuration, and some more administrative stuff. This does not mean that the aggregate, which is commonly named aggr0 of the node, does not fail over in case of a node outage, or upgrade, or any other reason why the node is down. It will fail over like any other aggregate, but it is not for client data. Well, that's the important takeaway. So in the end, you usually have at least 2 aggregates per node, the root aggregate and a data aggregate. By the way, the natural state of being of a drive flows from being unowned to spare when it's assigned to a controller, and a spare will turn into a data disk when it replaces a failed drive in a RAID group, or when it's used to create a brand new aggregate or grow an existing aggregate. There's one very important note to be made here. When you add a disk to an aggregate, you better make sure that it's really what you want, because you will never be able to remove the drive from the aggregate other than destroying the aggregate completely. Another important feature with regards to drives is that the drives can be partitioned into a small partition for the root aggregate and 1 or 2 data partitions. This provides for better space usage of the drives and also for wider RAID group sizes. We're not going to go into details here, but simply keep in mind that this partitioning is referred to as advanced drive partitioning and is primarily beneficial for usable data space. And finally, when an aggregate is created, it will have a file system in it. The ONTAP file system is called WAFL, or Write Anywhere File Layout. Now this is a Unix type file system, and in a second we will introduce flexible volumes, which will have an administrative starting point inside this WAFL file system. Hence, the single flexible volume cannot span multiple aggregates, because the file system is always limited by the aggregate. Now we've looked at what an ONTAP node is and how two nodes can be connected together via an HA interconnect to form an HA pair, and that you can create a cluster that is formed by a single node or by a single HA pair or multiple HA pairs. And for running multiple nodes in a single cluster, you always need a cluster interconnect network to form the cluster. We've also seen that drives can be assigned to a node, which will turn those drives or partitions into spares, which can then be used to automatically replace broken disk or to create and grow aggregates based upon one or more RAID groups with a parity type of RAID 4, RAID DP or RAID Tech. But of course what we are ultimately interested in is how to store data on the aggregates. Well, that is where flexible volumes come in. A flexible volume is part of the aggregate file system, which is called WAFL. And every volume gets a starting point in the aggregate by means of something which is called the root inode of the volume. This single inode holds the metadata of the volume as well as pointers to data blocks that allow users to store files in the volume. Now, volumes can be grown and shrunk when needed. They can be thin provisioned, which means that they do not reserve any space in the aggregate up front, but only start taking space when actual blocks are being written into the volume. Volumes can be cloned for reasons we will see later, and of course volumes can be deleted. The thing is that if you want to create volumes, you will need a virtual entity that will own the volume, because volumes are not floating around. They need something which is called an SVM, or storage virtual machine. Now it's very simple. A storage virtual machine runs cluster wide, so every node in the cluster is able to connect resources to the SVM. And you can have many SVMs. To make it even simpler, there are basically only two resource types that need to be connected to a storage virtual machine. And those are flexible volumes, as I mentioned, and logical interfaces. Now in short, a logical interface is a construction that holds an address with lots of properties. So on the one hand we have the clients that connect to a particular LIF, and on the other hand we have the flexible volume on which they can store their data. And it's the SVM that connects both of them together. Keep in mind that you cannot create either LIFs or flexible volumes if you have no SVMs in place. So NAS protocols as well as SAN protocols all need LIFs to be able to access the volumes which are hosted by the same SVM. To be honest, it's all about storage virtual machines. So an SVM runs storage protocols like NFS, iSCSI, etc. An SVM has one or more volumes, and an SVM has one or more LIFs to make those volumes accessible. Next to these data SVMs, there's also a single SVM for every node in the cluster, and a single SVM for the entire cluster. These SVMs are used for management, and they're not used by data clients. With regards to data volumes, there's an important distinction to be made. Data volumes that are used for NFS or SMB protocol are always mounted to be accessible by clients, so you have to mount the volumes. The mounting of data volumes is done by connecting them to a junction path or a mount point, which usually gets created on the root volume of the storage virtual machine. Please do not confuse the root volume of a storage virtual machine with the root volume of a node. Remember, the root volume of a node, or vol 0, is used for storing configuration data and log files, and the root volume of a storage virtual machine is only 1 GB in size, and it is there for junction paths, so that clients can access the actual data volumes. The term that's used for all the mounted NAS volumes in an SVM is referred to as the SVM namespace. SAN volumes, so volumes that host SAN LANs, do not need to be mounted. So in summary, there are SVMs that are there for management purposes, and there are data SVMs which are there for having volumes that contain client data. The data can be made accessible by creating a resource type which is called a LIF, or a logical interface, and we will look at networking right after this. NAS volumes will have to be mounted to be accessible by clients, and all mounted volumes together form the SVM namespace. And finally, SAN volumes do not have to be mounted. Now, with regards to networking, there are some specifics you should be aware of. First, of course, there are the lifts, which can allow clients to connect so as to be able to get to the data volumes. The lifts are the logical part, whereby NAS lifts can fail over from one node to any other node in the cluster, and SAN lifts cannot fail over. So SAN lifts will never fail over. That's a very important thing to keep in mind. So every node in the cluster that should be able to run a SAN protocol will need a lift to provide access to the LUN that is hosted by the particular node. So SAN lifts will not fail over between nodes, but NAS lifts by default do. Next to logical network interfaces, there are also virtual ports like VLAN ports and interface groups. An interface group is like a port channel that can have multiple physical ports connected to it for bandwidth and redundancy purposes. And at the bottom of this schema, there are physical ports. So it's physical ports that host the virtual ports, and lifts are configured on top of VLAN ports, interface groups, or even directly on physical ports. A common usage of all of these ports would be to create an interface group of 2 physical ports and configure a VLAN port on top of the interface group, and then configure a lift on the VLAN port. And to finish this off, let's go back to the cluster interconnect. These lifts, which are not data lifts, are dedicated for the cluster interconnect network. These lifts should be configured directly upon dedicated physical ports, like this. And finally, with regards to networking, there are IPspaces and broadcast domains. An IP space defines a distinct IP address space in which storage virtual machines reside. So when you create an SVM, it will always be connected to an IP space. By default, this will be the available default IP space, and an SVM will only be able to host lifts in that particular IP space. And after having set up a cluster, you will always have a minimum of 2 IP spaces, one IP space for the cluster interconnect and another IP space for the data SVMs and for management. Very often this is all you will need. The only reason why you should create more IP spaces than the available default is when you have different customers that have overlapping subnets. So for example, if you have 2 customers that want to use the same subnet, then you should definitely create at least one additional IP space so that ONTAP knows where to route its packets. So to make a long story short, IP spaces are equivalent to virtual routing and forwarding, a technology that allows multiple instances of a routing table to coexist on the same piece of networking infrastructure. So how can we use IP spaces? Now, every IP space needs a minimum of 1 broadcast domain that holds the physical and/or virtual ports you use to configure lifts upon. Having said that, a broadcast domain is also a failover group. This means that any lift connected to a port in a particular broadcast domain can fail over to any other port in the same broadcast domain, with the exception of SAN lifts, of course, because SAN lifts, as we know, do not fail over. So for example, a lift that is hosted on a VLAN port should not fail over to a physical port or to an interface group. So the solution would be that you create multiple broadcast domains that only contain VLAN ports of the same VLAN, so that you're sure that at failover time the connection will not fail because of lack of VLAN availability. So in summary, the creation of additional IP spaces is only necessary when you have to allow for overlapping subnets. And the creation of multiple broadcast domains in a single IP space is very common because it guarantees the correct failover of lifts. And next to physical ports, we have interface groups and VLAN ports. And finally, there are lifts or logical interfaces which contain an address for clients to access the storage. Now, we've seen that client data will be stored in flexible volumes, but how do we protect these volumes? At the heart of ONTAP data protection lies the snapshot. A snapshot is a point-in-time copy of the root inode of any particular volume. We've already seen that the root inode is the administrative starting point of the volume, and a snapshot is a read-only copy. So a single volume can have up to 1023 snapshots. Now, a snapshot is not a backup, even though it is sometimes referred to as a local backup copy, so that it can be used to restore accidentally deleted or modified files. But if you lose the volume, you also lose the snapshot. So it is not a real backup. Having said that, snapshots are very useful when creating actual backup copies or disaster recovery solutions. In this overview, we'll have a quick look at some of these solutions. The most important tool for replicating data is called SnapMirror. In most cases, SnapMirror uses snapshots to incrementally replicate snapshotted blocks from a source volume to a destination volume in the same storage virtual machine, another storage virtual machine in the same cluster, or, and this is most common, to a volume in a different SVM in a different cluster. These SnapMirror relationships can be for disaster recovery, so for failover purposes. In the case one site goes down, the destination site can be activated, or the relationship will build retention on the destination site so as to keep many snapshots as backups that can be restored from the destination to the source site. And with disaster recovery relationships, you have two options, namely synchronous or asynchronous, meaning that if it is a synchronous SnapMirror, all data will be sent to the destination before the client is acknowledged, which means that there will be no data loss when the source fails. In an asynchronous relationship, these snapshotted blocks are replicated on a scheduled basis, which simply means that you will always lose data if the source fails. And the amount of data that you lose will depend on the frequency of replication. And famous solutions for zero data loss because of the synchronous nature are SnapMirror ActiveSync and MetroCluster.